This section of chemical kinetics discusses rate laws. So we've already seen how the concentration of a reactant decreases over time or a product increases over time. We're going to use that information to write rate law equations. So consider the homogeneous reaction between the ammonium ion NH4+ and the nitrite ion NO2 with a -1 charge as shown in the reaction below. A series of 6 experiments were carried out, and you can see that the initial concentration of ammonium and the initial concentration of nitrite ion are varied over the experiments. So in experiments 4, 5, and 6, the concentration of ammonium is held constant at 0.2 molar, while the concentration of NO2 is varied here. In the first 3 experiments, the concentration of NO2 remains constant, while the concentration of NH4+ is varied. So the question we want to try to answer by looking at the data here is how does changing the concentration of the reactants affect the rates? So let's look at experiment 1 and 2 here for a minute. Because the concentration of the NO2- is being held constant, we can say what the effect of changing the concentration of the NH4+ is. So we double the concentration of the NH4+ in going from 0.01 to 0.02 molar. And in doing so, what happened to the rate of the reaction? It went from 5.4 to 10.8 times 10 to the -7th molarity per second. So when we doubled the concentration of the ammonium ion, we also doubled the observed initial rate of reaction. Okay, a similar thing happens down here. Let's look at experiment number 5 and 6. Again, when we hold the concentration of the ammonium constant at 0.2, but instead change the concentration of the nitrite, NO2- ion. So if I double the concentration of the nitrite from 0.0404 to 0.0808, what happens to my rate of reaction? It goes from 21.6 to 43.3 times 10 to the -7 molarity per second. So again, by doubling the concentration of that reactant, we also doubled the rate of the reaction. So doubling the ammonium doubles the rate of the reaction. Doubling the nitrite also doubles the rate of the reaction. Based on that data, we can conclude that the rate of the reaction is proportional to the concentration of each of the reactants. So the rate is directly proportional to the concentration of both ammonium and nitrite. And we can combine those two proportions into one to say that the rate is proportional to the concentration of ammonium times the concentration of the nitrite ion. In order to write a proportionality expression as an equation, all you need is some constant, some proportionality constant. So here I've just turned this proportion into an equation by adding the constant that you see here, K. Oops, excuse me. Let's undo that. The constant that you see, K. Okay? That K is called the rate constant, and the equation is called the rate law. The rate constant K is specific for a certain reaction at a given temperature. Okay? So we have a rate law equation that includes the rate constant and shows how the concentration of each reactant is proportional to the rate of the reaction. Because we have a direct proportionality where the rate doubles if the concentration doubles, we say that the reaction is first order with respect to each of the reactants. So it's first order with respect to ammonium and first order with respect to nitrite. The overall reaction order can be found by adding the exponents on the reactants in the rate law. So in this case, what is the order of the overall reaction? Well, the exponents in each case are a 1 because we have a direct proportionality. And so if I add those two exponents, 1 plus 1, I get a 2. So we say that this reaction is second order. Okay, overall second order reaction. What that means is if I doubled the concentration of both reactants, then the rate would quadruple.